pure distilled insight. Today, we're diving headfirst into, well, one of physics' most mind-bending questions. Is reality fundamentally geometric? Where space-time is this fixed stage dictating all the rules? Or is it fundamentally physical, with information-carrying waves actually defining the very geometry we perceive?
It's a huge question. It really cuts right to the core of what the universe is made of. And we're exploring excerpts today from a fascinating analysis called the Wave-Centric universe, Relativity from Wave Propagation.
Right. So our mission today is to unpack this powerful, almost intuitive idea. The idea that everything we know, I mean, from distant starlight to the forces holding atoms together, it's all communicated by fields and waves. And the really intriguing part, the suggestion is that the rules governing this communication process are the rules of reality itself. We're going to try and deconstruct some of those iconic relativistic effects like time dilation.
Yeah, it's weird stuff.
Exactly. And reinterpret them not as these abstract geometric paradoxes, but as maybe direct, necessary consequences of how waves just move and interact.
It's quite a journey, actually. It traces a line from a genuine crisis in classical physics all the way to the frontiers of modern thought, where relativity itself might just be an emergent property of something even more fundamental.
Okay, let's unpack this then. Our journey to relativity didn't actually start with abstract geometry or, wild theories about space-time. It began with very concrete physical problems. Problems related to how waves, specifically light waves, actually propagate. And for that, we need to go way back. Christian Huygens, 1678.
That's right. And what's really foundational about Huygens' principle is its simplicity, but it has this profound impact. He basically proposed that every point on a wavefront, like imagine a ripple in a pond, acts as a source for new, tiny spherical wavelets.
Little waves spreading out from every point.
Exactly. And the wave's position just a moment later, it's simply the sum, or the envelope, you could say, of all these little wavelets combined.
So, if I'm getting this right, that's maybe the first time anyone really formalized the idea that the experience of any point in space isn't global. It's defined purely by its local role. Receiving information from the past through these waves and then contributing to the future by emitting its own.
Precisely. So the big picture, the global wave behavior, it just emerges from all these collective local actions, which is pretty insightful for the 1600s.
No kidding.
And yeah, this concept was later refined. Huygens-Fresnel showed how these wavelets interfere, explaining things like diffraction. Gustav Kirchhoff gave it a solid mathematical basis, and modern physics even tweaks it further, like treating wavelets as dipoles, which naturally cancels out any backward propagation. So it builds on that core idea.
But the real game changer, the moment that truly set the stage for the relativity revolution that arrived with James Clerk Maxwell in the 1860s, he did something incredible, right?
Yeah.
Unifying electricity and magnetism.
A monumental achievement. He brought them together into this single, elegant set of equations. And what those equations predicted was, well, it was startling. The existence of self-propagating electromagnetic waves. Waves that would always travel at a specific unyielding speed in a vacuum. A speed we now call c.
And the speed wasn't dependent on anything else.
No, purely determined by fundamental constants of empty space itself, the permittivity and permeability, things inherent to the vacuum.
And here's the kicker. That calculated speed perfectly matched the measured speed of light, so the conclusion was inescapable. Light is an electromagnetic wave. Huge. But this amazing discovery immediately created a profound, unavoidable crisis for physics.
Exactly, because Newton's classical physics, based on Galilean relativity, said velocities just add up. Simple addition. So if you shine a flashlight from a moving train, its speed relative to the ground should be the speed of light plus the train speed, c plus v.
Makes intuitive sense.
Right. But Maxwell's equations, which were being confirmed by experiments, insisted the speed of light is always c, period. Doesn't matter how fast the source is moving. This was a head-on collision, an irreconcilable contradiction born directly from the properties of waves. It was the crack in the foundation that forced us to rethink everything.
So this conflict basically forced a choice.
Yeah.
Either Maxwell's equations, this incredible unification, were somehow wrong, or our centuries-old understanding of space and time was fundamentally flawed. And history tells us the properties of waves won out. It compelled this brand new, almost alien description of spacetime.
And the crucial insight here, the mathematical core, is that the entire framework of special relativity can be derived directly from a single powerful demand, which is the laws governing waves must remain consistent for all observers no matter how they're moving.
Okay, so like a universal rule for waves.
Sort of. Think of it like this. There's a specific mathematical way to describe a simple the wave equation. It's like a universal recipe for how waves behave.
And if the laws of physics are truly the same for everyone, whether you're standing still or whizzing by in a spaceship.
Then that wave recipe has to look identical to both observers.
Yeah.
It has to have the same mathematical form.
That seems logical, yeah.
It does. But that seemingly simple requirement has absolutely staggering consequences. By just insisting that the form of this wave equation remains invariant, you are mathematically forced to derive the Lorentz transformations.
Forced, not just suggested.
Forced. It's not a choice. It's what the math demands. It's like the universe saying, look, if you want light to always travel at sea for everyone, then space and time have to warp in this very specific way. And those Lorentz transformations are the structure of relativistic spacetime. That's where the intertwining of space and time comes from, emerging directly from requiring consistency for wave propagation.
Wow. That's a huge paradigm shift right there, because our everyday intuition, Galilean transformations, that tells us time is absolute. T prime equals T. A second is a second for everyone, and distances are fixed. A meter is a meter. But Lorentz says no. Time itself transforms. It depends on your motion. And it's this combined thing, the space-time interval, that stays the same for everyone. So it's not just fiddling with equations. It means our gut feeling about a universal now or a rigid ruler is just wrong when things move fast. It forces us to see time and space as woven together like a fabric that can stretch and bend.
And if you connect this back to Einstein, this reevaluation even touches on his own postulates. He famously based special relativity on two axioms, right? The principle of relativity laws of physics are the same for everyone, and the constancy, the speed of light, is the same for everyone.
Right, those are the two big ones.
But from this wave-centric viewpoint, that second postulate, the constancy of light speed, well, it doesn't look quite like an arbitrary axiom anymore. It looks more like a direct physical consequence of Maxwell's theory. It's a property inherent to light waves themselves, something already established before Einstein formalized SR.
Ah, so Einstein's genius wasn't just stating that light speed is constant.
His genius was in generalizing that lesson. He took the specific property observed in electromagnetism and elevated it. He said, this principle of invariance must apply to all physical laws, not just light. So relativity becomes this theory that's deeply motivated by how light behaves, revealing a fundamental truth about reality's structure.
This also brings us back nicely to that earlier idea you mentioned, the unique experience at each point in space, defined by the waves arriving there. That intuitive concept actually gets a precise mathematical form, doesn't it? Something called the light cone.
Exactly. For any event, and think of an event as just a specific point in space and time, like a firecracker going off right here, right now. Its light cone neatly divides all of space-time into three distinct regions relative to that event. There's the past light cone. Everything that could have possibly influenced this event, sending signals to it at or below light speed.
Okay, the causal past.
Right. Then there's the future light cone. Everything this event can influence, sending signals out from it. And then there's, well, elsewhere. All the points in space-time that are too far away in space and too close in time to either affect or be affected by our event, they're causally disconnected.
So you can't get a signal there and they can't get one to you in time.
Correct. And an observer's path through space-time, their world line, has to always stay within these light cone boundaries. Why? Because nothing travels faster than light. You can't outrun your own light cone.
So what this really means for you, listening, is that the information available to you right now is entirely defined by what's within your past light cone. The entire causal structure of reality, what can influence what is fundamentally dictated by the geometry of how waves propagate. It's all about the signals reaching you.
Now, let's look at how those famous, seemingly bizarre consequences of special relativity, time dilation, length contraction, the relativity of simultaneity, how they start to look remarkably intuitive, almost logical, when you view them as outcomes of a universe where information travels as waves at this finite, constant speed c.
The relativity of simultaneity is a great place to start. It really messes with your head. The idea that at the same time, for events happening far apart, isn't an absolute fact. It's just a convention. It depends on the signal speed.
It absolutely depends on the signal speed, which is finite. Let's use the classic thought experiment. The train and the lightning strikes. Imagine an observer standing on a platform exactly halfway between 2 points where lightning strikes the track, say at the front or back of a passing train.
Okay, standing still on the platform.
Right. They see the light waves from both strikes arrive at their eyes simultaneously. So naturally, they conclude the strikes happened at the same time. Simultaneous.
Seems reasonable.
But now consider an observer on the moving train. also sitting exactly midway between the front and back where the lightning hits. This observer is moving towards the light wave coming from the front strike and moving away from the light waves coming from the back strike.
Ah, okay, their motion relative to the light paths is different.
Crucially different. And because the speed of light is still c for this moving observer too, that's the key rule, the wave from the front, the one they're moving towards, reaches them first. The wave from the back has further to catch up, relatively speaking.
So the train observer concludes the front was struck before the back.
Exactly. And they're both right from their own perspectives. This isn't an illusion or a mistake. The disagreement about simultaneity is a direct, unavoidable consequence of the physics of wave propagation and that constant light speed. Their different states of motion simply lead to different arrival times for the information. It really shatters that idea of a universal now.
Wow. Okay. What about time dilation? The whole moving clocks run slow thing.
That one can be understood really nicely with the light clock thought experiment. Imagine a very simple clock. A tick happens when a light pulse bounces vertically between two mirrors, say distance L apart. For a clock just sitting there at rest, the time for one tick is easy. Distance divided by speed. So 2L divided by C. Let's call that delta T0.
Oh, it's simple enough.
But now, let's watch that same clock as it moves horizontally past us at some high speed, φ2. From our stationary viewpoint, we see that light pulses travel a longer diagonal path up to the top mirror and then another diagonal path back down.
Right, because the mirrors have moved sideways while the light was in transit.
Exactly. And here's the absolute key. The speed of that light pulse for us watching it is still c. That rule doesn't change. So if the light has to travel a longer distance, the diagonal path at the exact same speed, c speed, it must take longer to complete the journey.
Longer distance, same speed. Means more time.
Precisely. So the moving clock's tick, delta t, as measured by us, is longer than the tick of the stationary clock, delta t0. The moving clock appears to run slow. This isn't some trick of perception, it's a real effect. Time itself flows differently depending on motion, ensuring c stays constant for everyone. It's why particles in accelerators literally live longer than identical ones at rest. Their internal clocks are ticking slower.
Okay, that actually makes a kind of kinematic sense.
Yeah.
What about length contraction? Objects getting shorter in the direction of motion.
Length contraction is often explained as a kind of corollary to time dilation and the relativity of simultaneity. Because, think about it, to measure the length of a moving object, you need to determine the position of its front and back ends simultaneously.
Ah, and we just established that simultaneously is relative.
Exactly. So, since observers in different frames disagree on simultaneity, they'll also disagree on the measured length. That's the standard geometric explanation.
But is there a more physical, wave-based way to think about it?
There is, and it's quite fascinating. Drawing on de Broglie's hypothesis, the idea that all particles, and therefore all matter, have wave-like properties. The suggestion is that for a moving object, its constituent de Broglie waves, these fundamental matter waves, actually get compressed in the direction of motion.
Like a Doppler effect, but for matter waves.
Sort of, yes. A kinematic compression. This compression causes the fundamental wavelengths that define the spacing of atoms within the object to become physically shorter along the direction of travel. So the entire object contracts. It's not just an appearance. It's arguably a physical compression of the matter's underlying wave structure.
That's a very different picture.
It is. And this interconnectedness of effects is beautifully shown by something seemingly unrelated. The magnetic attraction between two parallel wires carrying current. You can actually explain this magnetic force purely using electrostatics and relativity.
How does that work?
Well, if you shift your perspective to the reference frame of the moving electrons in one wire, from their point of view, the stationary positive ions in the other wire are moving past them. And because those ions are moving, their spacing appears lengths contracted.
Okay, the wire itself looks shorter or denser from the electron's view.
Denser with positive charge, yes. The ions are packed closer together due to length contraction. This higher positive charge density creates a net electrostatic attraction for the moving electrons in the first wire. What we perceive as a magnetic force in the lab frame becomes a purely electrostatic force, modified by relativistic length contraction in the electron's frame. It's a stunning example of how these effects are woven together, rooted in charge and wave propagation.
Okay, so just to quickly recap these wave-based takes, relativity of simultaneity happens because information carried by waves at speed c simply arrives at different times for different observers. Check.
Mm.
A time dilation happens because light, always at sea, has to cover a longer path in a moving clock, which just takes more time. Check. Length contraction can be seen as a physical squishing of the de Broglie wavelengths that make up matter. Check.
A plausible physical interpretation, yeah.
Yes, and even EM-Sibako, you mentioned this earlier, can be thought of as mass being the energy locked up in some kind of underlying wave structure of a particle when it's at rest, maybe like a standing wave.
That's one intuitive way to picture it, yes.
Yeah.
Mass as the energy of the wave's internal dynamics, perhaps its circulation or oscillation in its rest frame.
All right, so special relativity deals with constant velocity, waves in a, let's say, static medium. How does general relativity fit into this wave-centric picture?
General relativity, GR, essentially takes this to the next level.
Yeah.
If SR is about waves in a static medium, GR describes a dynamic medium. It tells us that the rules of wave propagation, the very structure of spacetime, are actively shaped and altered by the presence of matter and energy.
And this huge leap started with Einstein's famous happiest thought, the equivalence principle.
Yes. The realization that the effects of a uniform gravitational field are locally indistinguishable from the effects of uniform acceleration. Think about being in an elevator in deep space, accelerating upwards. You'd feel pressed to the floor, just like gravity. Or, conversely, if the cable snaps on Earth, you feel weightless inside the falling elevator.
Locally, you can't tell the difference.
You can't. And the profound implication Einstein drew was that gravity isn't a force, in the traditional sense, pulling objects through space. Instead, objects under gravity are actually following the straightest possible paths called geodesics through a curved spacetime.
So free fall isn't being pulled, it's just following the natural contours of space-time.
Exactly. Free fall is the most natural motion.
Hmm.
Our feeling of weight standing here on Earth, that's just the ground pushing up on us, preventing us from following our natural geodesic path downwards through curved spacetime.
Okay, that fundamentally reframes gravity, and the math behind this is the Einstein field equations, often written G equals kappa T.
That's the concise form, yes. G represents the geometry of spacetime, its curvature. T represents the distribution of matter and energy within that spacetime. Kappa is just a constant linking them. It's this beautiful equation that shows how spacetime geometry and matter-energy content dictate each other.
So from the wave-centric view, how does that equation look?
You can see it as describing this dynamic feedback loop. Matter and energy, which, remember via E-MC theories, we can think of as localized concentrations of wave energy, tell spacetime how to curve. And that curvature, in turn, tells all subsequent waves and particles, including light and matter waves, how to propagate, which paths to follow. It's precisely what physicist John Archibald Wheeler summed up so well. Space-time tells matter how to move. Matter tells space-time how to curve.
And we see this playing out in observations, right? Like gravitational lensing.
Absolutely. Gravitational lensing is a prime example. Light from distant stars or galaxies appears bent when it passes near a massive object like another galaxy or a black hole. It's not that gravity is pulling the light sideways, it's that the light waves are following their geodesics, the straightest possible paths, through space-time that has been warped or curved by the massive object's presence. The wavefronts themselves get distorted.
Like space-time itself is acting as a lens.
A cosmic lens, yes. And then there's gravitational time dilation and redshift. We know clocks tick slower and stronger gravitational fields. That's gravitational time dilation. And as light climbs out of a gravitational well, it loses energy. For a wave, losing energy means its frequency decreases and its wavelength stretches. We observe this as gravitational redshift. These are direct, measurable effects of curved geometry impacting the fundamental properties of waves.
And the ultimate confirmation, perhaps, are gravitational waves themselves.
The ultimate confirmation, indeed. These aren't just waves traveling through space-time, they are ripples, disturbances in the fabric of space-time itself, propagating outwards at speed sec from violent events like merging black holes. They are direct proof that the propagation medium, space-time, is active, dynamic, and can be disturbed in it. It has its own wave dynamics. It proves the causal structure itself can ripple.
Okay, so we've built up quite a case here, historically, mathematically, and intuitively through these effects for seeing relativity as deeply rooted in wave propagation. But this brings us to a really fundamental, almost philosophical question, doesn't it? Is relativity ultimately a principle of geometry where space-time is this pre-existing stage and wave mechanics just has to conform to its rules? Or is the stage itself kind of an illusion, a property that emerges from the way waves behave?
That's the core tension, yeah. The standard physics interpretation, broadly speaking, leans towards geometry. It generally treats the postulates of relativity as fundamental principles governing spacetime. And all physical theories, including quantum mechanics and wave mechanics, must be formulated to respect that geometry.
Spacetime first, waves follow.
That's the conventional hierarchy, yes. But the idea of emergent spacetime, especially coming from quantum gravity research, really challenges that. It asks if there's a deeper layer underneath.
What kind of ideas are we talking about there?
Well, many modern theories trying to unite gravity and quantum mechanics explore the possibility that spacetime, and maybe even gravity itself, aren't fundamental. They might emerge from something more basic, perhaps related to quantum information. For instance, there's some really radical, speculative ideas like ER-EPR, suggesting spacetime geometry is somehow built from patterns of quantum entanglement between particles.
Entanglement creating space, how would that work?
The rough idea is that more entanglement between quantum systems might correspond to them being closer in some emergent geometric sense. Gravity could then arise as changes in energy distribution alter these entanglement patterns, thus changing the emergent geometry.
Wow. Okay, that's pretty out there.
Definitely out there. Another related idea is entropic gravity, which suggests gravity isn't a fundamental force, but an emergent phenomenon related to thermodynamics and information. Like, it's a statistical tendency, an entropic force, pushing things towards arrangements that maximize entropy.
So gravity as bookkeeping.
The very loose sense, maybe. But it's absolutely crucial to stress these are highly speculative research directions. They're theoretically fascinating, mathematically complex, but currently lack direct experimental proof. They're frontiers of thought.
Now, interestingly, you mentioned there's a wave-based theory that doesn't automatically lead to relativity, the de Broglie-Bohm pilot wave theory.
Yes, and that's a really important counterpoint. It shows that just having waves isn't enough. Pilot wave theory posits real particles, always guided by a real physical pilot wave. It's fundamentally wave-based. But to make its predictions match experiments, it requires some pretty extreme things. Profound non-locality, instantaneous connections across space, and critically absolute simultaneity.
A universal now.
A universal now, yes.
Yeah.
A preferred reference frame where events are truly simultaneous. And that directly contradicts the core principle of special relativity, which abolished absolute simultaneity. So the lesson from pilot wave theory is clear. Just having a universe full of waves doesn't guarantee you get relativity. The waves themselves must have very specific properties that they need to be Lorentz covariant. They need to have the rules of relativity sort of built into their own structure, rather than imposed by an external space-time stage.
Which loops us back to maybe a more direct, more elegant formulation of this whole wave-centric idea.
Exactly. What if we tried a single postulate? Something like, all fundamental matter consists of waves that intrinsically propagate at speed c.
Just waves, always moving at c.
Fundamentally, yes. Particles, in this view, are just localized wave packets or solitons, stable, bundled-up wave structures. A particle's observed velocity, the fact that we see it moving slower than c, is simply the group velocity of its wave packet, how the overall bundle moves. But its underlying constituent waves, the phase velocity, might always be c.
Okay, and what about mass?
Rest mass, m0, could be interpreted as the energy contained in some kind of internal motion of the wave, maybe a circulating component, or a standing wave pattern when the packet as a whole is at rest.
And does this picture hold together mathematically?
Remarkably well, proponents argue. From this single postulate about matter being c-speed waves, you can naturally derive the famous energy-momentum relation. E squared equals bc squared plus m0c squared. And you can even derive the Lorentz transformations themselves by considering how different observers would measure the properties, like frequency and wavelength, of these fundamental matter waves. So this model offers a concrete, self-consistent physical picture where relativity emerges from the inherent properties of waves without needing to postulate a non-Euclidean geometry first. So, wrapping this up, it seems the connection between wave mechanics and relativity isn't just incidental, it looks foundational. We saw the historical push came directly from wave physics with Maxwell. The mathematical structure, Lorentz transformations, can be derived from demanding wave invariance, and all the major weird consequences, time dilation, length contraction, simultaneity, become almost logical outcomes of wave kinematics, of how information travels. It paints a very compelling picture, highlighting that deep, perhaps underappreciated link.
Which leaves us wrestling with that profound tension. Does space-time geometry dictate the rules for waves? That's the standard view, more or less. Or do the fundamental properties of waves themselves actually define the geometry of space-time we experience? While physics textbooks largely lean the first way, this deep dive has shown you the power, the coherence, and maybe the growing relevance of that alternative wave-centric perspective.
Right. This exploration doesn't definitively answer whether reality is ultimately geometric or informational or wave-like. Perhaps it's a mix, or something else entirely. Instead, hopefully it leads you right into the heart of one of science's deepest, most exciting ongoing quests, to truly understand the fundamental nature of our universe. What stands out to you about this wave-centric perspective? What questions does it raise for you?